here is a function. X to the fourth minus 3x to the negative 5 halves plus 8x to the sixth. Don't write this down, by the way. Minus 1/2 x to the 4/3 times 2x plus 5 minus 7x to the fourth plus 3x to the negative 2. How do you like that function? Pretty good function? Yeah? Yeah, pretty good function. I want its derivative. What are you going to have to do to find the derivative of that?
Spend more than 5 minutes of your life.
What was that? Sit through 5 minutes of my lecture? More than 5 minutes of my lecture?
Oh, yes, spend more than 5 minutes of your life on it.
Oh, of your life. Oh, yeah. It's going to take you a little bit of time there. It's going to be a painful process to distribute all of that out. Do you guys agree? Yeah, I mean, you have to distribute it all out to get into like that form of the pluses and the minuses for the power rule. True? And
yeah, it's not.
Yeah, that would really suck. So what we're going to do about this is we're going to say this sucks. Yeah, and we're going to not do that. What we're going to do is we're going to develop a rule that will allow us to take the derivative of something similar to this, where it's a function times another function. In fact, we're going to call this function the function u, and we're going to call this function the function v. You'll be able to tell the difference between my u's and v's because my u's always will have this little tail on them and my v's will not. Because when I used to write them like this, that was a u and that was a v, and it was very confusing to people. So I retrained myself to make a u and a v. So we're going to use lots of u's and v's today, and we're going to deal with this thing that sucks. And we're going to deal with it by using something called the product rule. But before we can use the product rule, we have to figure out what the product rule is. And here it is. We're going to derive it in a second, but this is what the product rule is. It says that if I have two functions, u and v, that are being multiplied together, and I want to find the derivative of that product, just like we had in the previous one, right? U times v, then all I have to do is take the first function, u, multiply it by the derivative of v, and then add v times the derivative of u. That's the product rule. You're going to memorize that rule. It's exceptionally important. You will use it hundreds of times this school year. So memorize it as soon as you can so that you don't have to keep looking back and forth between your notes and the lecture and all that stuff to remember what it is. So we are going to derive it by using the limit definition of the derivative. So the limit definition of the derivative says, take the function that you're looking at, in our case, the function u times v, and write it out as the limit as h approaches 0 of that function evaluated at x plus h. So that'd be u of x plus h, v of x plus h, minus that function evaluated at x. That'd be u of x, v of x, all over h, right? That's you guys agree that that's the limit of the difference quotient of this function, u times v?
Yes.
Yeah? Okay, good. So just doing that by itself isn't super helpful because if I try to plug in 0 for h, it's indeterminate. And there's not really a whole lot that we can do to deal with that. So what we need to do is we need to introduce some extra terms in there. And we're going to add in a u of x plus h times a v of x, and we're going to subtract a u of x plus h times a v of x. Now, those seem like arbitrary terms to add and subtract in. They sort of are, but somebody a long time ago figured out that that worked out real nicely, and so now we all know that those are the right things to use. So it's okay to add and subtract the same term to a function. That doesn't change the nature of the function at all, right? It's just like adding in 0 if you add it and subtract it. but it does give us some other terms to work with. So we're going to have the limit as h approaches 0 of now a much more heinous, complicated looking, unpleasant function here. U of x plus h, v of x plus h minus u of x, v of x, plus u of x plus h, v of x, minus u of x plus h, v of x, all over h. Good or no? By your silence, I'll assume that's a yes. How does this help? What are we going to do? What's one of the ways that we've dealt with indeterminate limits in the past?
By factoring?
Factoring. All right, good. That's what we're going to do. We're going to factor some stuff out of here. But there's, in the numerator, are there any common terms between all four of these pieces? Remembering that u of x plus h is one term, v of x plus h is one term. Not the u is not a term separate from the x plus h. So I can't just factor u out of all of them, or just v out of all of them. So are there any common terms across all four pieces of that? You guys can all see the screen, right?
Yes, we can. I don't
Okay.
think common terms.
You don't think what?
I don't think there are any common terms in all of them.
You are 100% correct. There are no common terms across all four of those. So we're not going to be able to factor something out of all of it. So what we're going to have to do instead is we're going to have to separate it into two different limits and factor some stuff out of the two different pieces. So I'm going to help direct us here, since you guys are being very quiet today and not seeming like you want to put yourselves out there and make guesses about stuff. So I'm going to take this term and I'm going to take this term, and I'm going to put those two together as a single limit all over h. And I'm going to do the same with these two terms and put them all over h as a single limit also. All right, everybody okay with me telling you that that's what we're going to do?
Yes.
All right. So we're going to have the limit as h approaches 0 of u of x plus h, v of x plus h, minus, what's the one I said was going to go with that? U of x plus h times v of x. All over h. And then we're going to add to that the limit as h approaches 0 of the other terms, which we'll put the positive term first. Positive term is the u of x plus h v of x. Minus the u of x v of x all over h. So then take a look at those and see what you can factor out of the first limit and out of the second limit. So what can we factor out of that first limit?
U of x plus h.
So we're going to take a u of x plus h out of that. So we're going to have a limit as h approaches 0 of u of x plus h. And I'm going to just separate that out as its own limit times the limit as h approaches 0 of v of x plus h minus v of x all over h. Is it okay that I only put an h over the second limit there and not over the first one? Or under the second one, not under the first one?
Yeah.
Yeah, why is that okay? Because it's a multiplication between the two of them, right? So if it's a multiplication between the two of them, that denominator only really needs to be applied to one or the other. How come I put it with the one that I did put it with? And not with the other one? Do I recognize something about that?
Well, that's just the limit of v of x. Well, not just the derivative of v of x. Sorry.
Right, exactly. That's the limit as h approaches 0 of v of x plus h minus v of x all over h, which is the derivative of v of x. And so we're going to do a similar thing in the second piece of it. What are we going to factor out of the second piece of it?
V of x.
Yep, we're going to take out the v of x, and we will have a limit as h approaches 0 of just v of x, and a limit as h approaches 0 of u of x plus h minus u of x all over just the h again, only after the second one. Good? Which, as h approaches 0, what is u of x plus h equal to?
Just u of x.
Just u of x. And we already said that this one is the derivative of v. And then as h goes to 0, what's v of x? Should just be v of x. And then what's the second one there?
The derivative of u.
That one should just be the derivative of u of x. So we end up with that same thing that I told you was the product rule at the beginning. U times the derivative of v plus v times the derivative of u. Everybody good with that being our result there?
Yep.
All right, cool. That's how we derive the product rule. You do not need to memorize that. You just need to know what the product rule is and have it memorized, but I'm not going to ask you to derive it. So let's see if we can apply it to something like this. This one's not as bad as the first one that I said sucks, but we can still use the product rule in it. So let's do that. We'll call this function u, and we'll call this function v. So our derivative, f prime of x, should be u, according to the product rule, times the derivative of v, and what's the derivative of x squared plus 3?
2x.
2x, right, plus v, which is x squared plus 3, times our derivative of u, which is what?
3x squared.
2x squared. Good. Now, this answer here is okay. I got no problem with this being your answer. If you want to distribute it all out, that's fine. There are definitely plenty of occasions where it will be helpful within the context of the problem to distribute it out. But if you leave your answer as a derivative just like this, that's okay. Just be able to distribute it out. And in fact, let's distribute it out right now just so we can check, because we can check this by distributing this all out and using the power rule. So let's make sure it worked out and we get the same answer. 2x to the 4th plus 2x, if I distribute that, plus 3x to the 4th plus 9x squared, if I distribute that one. So 5x to the 4th plus 9x squared plus 2x. And if I had gone through at the beginning and just distributed this out to find the derivative, the distributing for this would have been x to the 5th, right? And then 3x cubed and x squared and 3. And what's the derivative of x to the 5th? 5x to the 4th. And the derivative of 3x cubed is the 9x squared, and the derivative of the x squared is the 2x. Everybody good or no?
Makes sense.
Cool. Now, you might be thinking, well, why didn't we just distribute this out? Distributing it out and using the power rule would have probably been easier than going through with the product rule. You're right, it would be. But for something like this, just using the product rule, if we don't need to distribute it out at the end to get like a one single long list of terms, it's a lot easier to just use the product rule. Plus, when I give you something later on, like, sine of x times x squared, well, there's no distributing that can be done there. You're just going to have to use the product. Everybody see why this is going to be helpful to us and get what we did there to get our result? That is a yes. Let's do another one. Why don't you guys see if you can get the product rule done for this function here. Take a minute or two and try to apply it. You guys finished with that or you need another minute? Finished or still working?
Still working.
All right. Are we ready now?
Yes.
All right. What was that?
We're ready.
Okay. So we should have u, which is x cubed plus 2, times the derivative of v, which should have been 2x plus 3, plus v times the derivative of u. Everybody good with that? Is that what you all got to start with?
Yeah.
I have sort of a different question. Is it okay if we put them in a different order? Like if it makes more sense to me to put it derivative of u times v plus derivative of v times u, is that okay?
Yeah, I mean you just have this term first and this term second. Yeah, that's fine. Doesn't matter. Yep, that is no problem at all. Do you guys distribute that out or no?
Yes.
Yeah.
All right, well, let's distribute it out. Make sure you guys got it right then. 2x to the fourth plus 3x cubed plus 4x plus 6 for the first one. And 3x to the fourth plus 9x cubed minus 3x squared for the second one. So 5x to the fourth plus, what do we got? 12x cubed minus 3x squared plus 4x plus 6. Yeah? Is that what you guys got?
Yes.
Cool. Any issues with that? Feel okay about the product rule?
Yep.
All right. I want you guys to find the derivative of this next one, and then we're going to work together to figure out the x values at which it has horizontal and vertical tangent lines. So this is x to the 1/3 times x squared minus 3x plus 2. So see if you can get the derivative. I'll give you two or 3 minutes. You don't need to simplify it down. Don't distribute everything out. So just use the product rule, and then we'll deal with it from there. So I'll just give you a minute or two for that. All right, you guys get your derivative?
Yes.
Okay. F prime of x should have been what? X to the 1/3 times 2x minus 3 plus 1/3 x to the negative 2/3 times x squared minus 3x plus 2. Everybody good with that?
Yes.
Okay. So then the question becomes, how do we figure out when this has horizontal or vertical tangent lines? Well, we know for horizontal tangent lines, we talked about that yesterday, right? The derivative f prime has to equal what?
0.
0. What about for a vertical tangent line?
Undefined?
Yeah, our derivative would need to be undefined because we know a vertical line has a slope that doesn't exist, a slope that's undefined. And so if the derivative is undefined, that means the tangent line is vertical. So anybody just looking at that see the values for all of that make that true? Values that make the derivative 0 and make it undefined? Probably not. You might see like one value that makes it undefined, but you probably don't see the values that make it 0 really easily. So how are we going to do that?
Well, the quadratic in the derivative, you can factor that, right?
The quadratic is a derivative. It's x minus 2 and x minus 1.
No, but like the second one, x squared minus 3x plus 2, can't you factor that and then you can like find the zeros?
Yeah, so you can factor the x squared minus 3x plus 2 to give you x minus 2 and x minus 1. But 2 and 1 aren't necessarily going to make the whole thing 0. It'll make this piece 0. But I still have something over here that I'm going to be adding to it. So it's not going to make the whole thing 0. You see what I'm saying?
Yeah, I get it.
Okay. So normally, if we're trying to figure out when something equals 0, usually it's with a quadratic, we factor it, right? And so that makes sense, but what we've actually got here is we've got one term plus another term. So what we need to do is we need to factor out the common thing between each of those. So what is the common thing between x to the 1/3 times 2x minus 3 and 1/3 x to the negative 2/3 times x squared minus 3x plus 2? Anybody see a common thing between those that could be factored out? No?
You factor out x to 1/3.
All right, that's an idea. Okay, I see an x to the 1/3 in there. Now let me ask you this. If I gave you this and said factor it, what would you factor out of it?
X squared.
Okay, you factor out the x squared, right? What if I gave you this? What would you factor out?
The x.
The x. What if I gave you this? What would you factor out?
X to the negative 1.
Right. We always factor out the smallest exponent, don't we? So I've got an x to the 1/3 and I've got an x to the negative 2/3. So how about instead of factoring out the x to the 1/3, we factor out the x to the negative 2/3? Let's see what happens with that. So x to the negative 2/3, when I take that out of x to the 1/3, what does that become inside the parentheses?
Just x to the 1.
Just x to the first power, because remember, if I distribute it back through, x to the negative 2/3 times x to the first, you would add those exponents and you should get x to the 1/3. So we got x times 2x minus 3 plus 1/3 of x squared minus 3x plus 2. And then we will want to drop this x to the negative 2/3 into the denominator and simplify what we've got inside the brackets on the top. Hold on one second. Okay, so as we drop that down, we end up with an x to the 2/3 in the denominator, and the x times the 2x minus 3 is 2x squared minus 3x, and this becomes 1/3 x squared minus x plus 2/3. Everybody good with that?
Yes.
Okay. And having these 1/3 is going to be a little bit of a pain. So could I get a common denominator of 3 for everything in the numerator and then drop that 3 into the denominator? I think I should be able to. So if I multiply 2x squared by 3 over 3, I'm going to end up with a 6x squared in my numerator. If I multiply the minus 3x by 3 over 3, I'm going to get minus 9x in the numerator. This one doesn't need to be multiplied by 3 over 3 because it's already got the 3 in the denominator. This will become a minus 3x and a plus 2, and then that 3 can go to the denominator with the x to the 2/3. Everybody good with that?
Yep.
Okay. We'll combine our like terms. So we'll have 7x squared minus 12x plus 2 over 3x to the negative 2/3. Okay. So when does this equal 0? That's our first question.
Wait, it's not to the negative 2/3, is it? Is it just 2/3?
Oh, sorry. Yeah, positive 2/3. Been writing negative 2/3 so much. It's positive 2/3. That's my fault.
Okay, thank you.
Yep. So when does this equal 0? what part of this fraction has to be 0 for the derivative? Just the numerator, right? If just the numerator is 0, then the whole thing will be 0, as long as those same x values don't make the denominator 0. So let's set the derivative 7x squared minus 12x plus 2 equal to 0. Does that factor? I'll take it by your silence that that means it does not, and we'll use the quadratic formula. So 12 plus or minus the square root of 144 minus, what is that, 4 times, yeah, it's 56, 4 times 7 times 2, all over 14. And that gives us 12 plus or minus root 88 over 14, or 12 plus or minus 2 root 22 over 14, or horizontal tangent lines at x equals 6 plus or minus root 22 over 7. Good or no?
Good.
Okay. And what about, this is our horizontal tangent lines. What about for our vertical tangent lines? When does this function, when is our derivative undefined?
When x equals 0, right?
Yep, when x equals 0, because that would make the denominator equal to 0. So it should have a vertical tangent line at x equals 0, and you should have horizontal tangent lines at x equals 6 plus or minus root 22 over 7. Any questions on that? All right. What if I gave you something like this? F of x equals x squared plus 1 over x squared minus 1. How would we take the derivative of that?
You
Use
could
the
write it.
product rule of the first one, like the first one times 1 over x squared minus 1.
Okay, it could be written like this, x squared plus 1 times 1 over x squared minus 1. And as you go through and try to use the product rule for that, you're going to need to know how to take the derivative of 1 over x squared minus 1. But we don't know how to do that yet, do we? I think once again, this sucks, doesn't it? It's kind of an unpleasant one. Wouldn't it be great if we had a rule for taking the derivative of the quotient of two functions?
That'd be awfully convenient.
It would be really convenient. And in fact, I think we could derive one right now. Here it is. This is the rule that you're going to memorize. It's called the quotient rule, but we'll real quickly derive it also down below. So the derivative of the quotient of two functions is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all over the denominator squared. And we're going to prove that by using a limit as h approaches 0 of the difference quotient of u divided by v, which should be u of x plus h over v of x plus h minus u of x over v of x all over h. Conceptually good with what we're about to try to do? Hopefully so. So the first step is we're going to get a common denominator we're going to simplify this complex fraction down. So the common denominator should be v of x times v of x plus h in the numerator. Would you guys agree with that? So if I get a common denominator between the v of x and the v of x plus h in the numerator, then I should be able to drop that into the denominator with the h. Do you guys agree?
Yeah.
All right, cool. So now this is similar to what we had before, but we got a similar problem in that nothing really factors out of this top. Plus I got some extra terms in the denominator. So I think we need to add some terms in. We're not going to use the same terms as last time. We're going to use just u of x, v of x. So we're going to add u of x, v of x, and subtract u of x, v of x in the numerator. So we got the limit as h approaches 0 of u of x plus h v of x minus u of x v of x plus h plus u of x v of x minus u of x v of x all over h v of x plus h. Everybody good with that or no? So now we're going to have to take some of them and combine them together. Anybody have any thoughts on which ones they want to combine together?
Maybe 1, 3, and then 2 and 4. I don't know if those numbers make any sense, but like the first one.
The first term and the first one and the third, or the first one and the fourth? I'm sorry, I couldn't understand what you said.
First one and the third.
Third, okay. First one and the third one. So those ones both have a v of x in them, right? So I would factor out the v of x if I were to do that. And what would I be left with? I'd be left with u of x plus h plus u of x. Is that going to be just like our derivative or no?
No.
No. So that one's going to be a little bit of an issue, which let's try a different one with the first one.
Factor it with the fourth.
Yeah, let's do the fourth one. And then I'll factor out the v of x. And what will be left is the u of x plus h minus a u of x. So let me give ourselves a new page here and do this. We got the limit as h approaches 0 of u of x plus h. What was it? U of x plus h v of x, right? Okay. Minus u of x v of x. I'm just going to put that over h for now, even though I know I have a v of x plus h and a v of x down there. Which two terms are left now? These middle ones, right? If I look at these middle two terms here, what do they have in common right now?
U of x.
Right, u of x. So if I take the u of x out, I'm going to get negative v of x plus h plus positive v of x. Does that give me the difference quotient thing that I need with the v of x plus h minus a v of x?
No, you have to factor out the negative.
We'd have to factor out the negative also. So let's do that. We'll factor out a negative u of x. So we're going to say minus, there's the negative being factored out. The limit as h approaches 0 of u of x. What do we have? U of x, v of x plus h, right? Minus u of x, v of x now. All over h. And then they both have the v of x and the v of x plus h down there. Everybody good there? Hopefully so. All right. We already said we're going to factor out the v of x from the first one. So this is going to give me a limit as h approaches 0 of v of x. And we're going to multiply that by a limit as h approaches 0 of u of x plus h minus u of x all over h. And what about this other part here? I've also got this v of x plus h that's down there. And so could I also put in that the limit is h approaches 0 of 1 over v of x plus h. Can I separate that by itself also? Should be able to. And then minus the limit as h approaches 0, and this one we're going to factor out the u of x. And we're going to still have a limit as h approaches 0 of v of x plus h minus v of x all over h. And I'm out of room there, but we're also going to have this limit as h approaches 0 of 1 over v of x plus h. Everybody following along with that?
Yeah.
Okay. So what's the limit as h approaches 0 of v of x?
V of x.
Okay. So we got v of x, and what's this one? This one is the derivative of u. And what's this one?
One over v of x squared.
Right, and so let's just put the v of x squared in the denominator. And then we have minus u of x, and then this is the derivative of v. And that's all going to be over another v of x squared, right? And since those both have the same denominator, we can combine them together into v, the derivative of u, minus u, the derivative of v, all over v squared. And that's the quotient rule that you're going to have memorized.
What are you doing?
Any questions on that or how we got to there? No? All right, let's see if we can apply it on a nice, simple, easy function here. So this is u over v, and so our derivative should be v times the derivative of u minus u times the derivative of v all over v squared. Any questions on that?
I have a question. So for the product rule, the order of like, since addition order doesn't matter, it like doesn't matter what order you differentiate or multiply in. But for this one, the numerator and the denominator functions matter, right?
Yeah, so I mean, it's got to be the right ones. Yeah, it's got to be denominator, derivative numerator, minus numerator, derivative denominator, over denominator squared. V du minus u dv all over v squared, where it's u over v. It's got to be the right ones. Yep. We'll be there. If we wanted to distribute this out just to see what it looked like, we'd get this. And that'd be our fully simplified version. Everybody okay with that?
Yes.
All right, let's do one more of those. You guys want to do this one on your own? And then we'll check and see if you got the same thing that you should have gotten. All right, take a minute or two. Don't bother to simplify this one. So just use the quotient rule to see if you can get it set up properly. So what do we think here? What should f prime of x equal? Somebody read out to me what they got. Anybody?
Um, 4x squared plus 5 times 6x minus 1 minus 3x squared minus x plus 2 times 8x divided by 4x squared plus 5 squared.
Excellent. So denominator, derivative of the numerator, minus numerator, derivative of the denominator, denominator squared. Any questions on that? I have no idea what you said. That was a bunch of static. I don't know if anybody else could hear you, or you could type it in the chat if it's not working on your mic. Hey, I got the chat to come up, so if you could type it in the chat, I should be able to answer your question. Yes, that answer is fine. You don't need to simplify that down. You should know how to simplify it down, and you should be able to distribute it out and combine your like terms, just in case I said, hey, when does this function have horizontal tangent lines? Then you'll need to be able to simplify that down to set it equal to 0. But that help? Make sense? Cool. Anybody else with that one, or are we ready to move forward? We got just a little bit more that we're going to do, and then we will be done. All right. we're going to do one more real quick rule. It's not going to require nearly as much work to prove it. And then we're going to apply it once, and then that will be it for the day. So our last rule is called the reciprocal rule. And the reciprocal rule is when we have a 1 in the numerator of our fraction for a quotient rule, or we could have like a 2 or a 3 up there. If I had a 2 or a 3 or a 7 up there, I'd just throw that 2 or 3 or 7 up here in the numerator with my final result. So the reciprocal rule is just an extension of the quotient rule. So the quotient rule says if I want to take the derivative of a quotient, which is what 1 over a function is, I do the denominator, which is g of x, times the derivative of the numerator, and the derivative of 1 is 0, minus the numerator times the derivative of the denominator, which is g prime, all divided by g of x squared, the denominator squared. And so we should see that this first term, no matter what the constant up here is, it's going to, when you take the derivative, it's going to become 0. That term will go away, and you're just left with negative g prime over g squared. So that's another good one to memorize and know. Note if this number was, like I said, a 2 or a 3, then as we do this, this would be a 2 or a 3, and then our final result would just have that 2 or that 3 out in front, or any other constant that we had out there. Good or no?
Yeah, it's good.
All right, let's apply it once, and then we will be done for the day. So this is a reciprocal rule problem, 1 over 2x cubed plus 5x. We should know then that f prime of x should be negative, and then the derivative of the denominator, which is 6x squared plus 5, over the denominator squared. And pretty simple and straightforward for that one. Any questions on that or anything else we've done so far today?
Could you go back to the last slide?
Sure.
I don't really get the explanation thing. Like,
Okay, so if we're taking the derivative of 1 divided by a function, we'll call it g of x. That's a function, because 1 is a function, right? Divided by another function. So we're going to use the quotient rule. So the quotient rule says denominator, so that's the g of x, times the derivative of the numerator. Derivative of 1 is 0. And then minus the numerator, which is our 1. And then the derivative of the denominator, the derivative of a function is just the derivative of it, g prime, divided by the denominator squared, right? That's what our quotient rule said, v du minus u dv over v squared. Good with that or no so far?
yeah.
Okay, and so then the function g of x, when you multiply it by the 0, that goes away, and you're just left with a negative derivative of g divided by g squared.
Okay, thank you.
Yep, I hope that helped. Any other questions on anything we've done today?
For the last one that we did for the quotient rule, the last example, how come we didn't solve it all the way through?
I mean, it's not required. I don't need you to simplify it all the way down. I know all your old math teachers probably said simplify, 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 but I have no interest in simplification. The AP test doesn't care if you simplify. They only care if, if within the context of the problem we need it to be simplified, that you are able to do that. So I assume you can all use the distributive property and combine those like terms. So I didn't bother with it. Yeah, it's not necessary for my class or the AP test, unless, like I said, unless the problem requires you to for some other reason. Like if I said, when does this derivative equal 0? Well, then you need to know when the numerator equals 0, and then you need distribute that all out and factor it further. That answer your question?
Yes, thank you.
Cool. You're welcome.
So just to confirm, in the final equation of the reciprocal rule, -1 times the derivative of g, not g to the first power.
Not g to a power. No, that's g prime, the derivative of g.
Prime, okay, over, is it g squared or the second derivative of g?
No, that's g squared. Yeah. Yeah, because remember the quotient rule says the second part or the end of your quotient rule is that denominator squared.
Oh, okay.
And so that's where we get that, because this is just us using the quotient rule to prove this rule. So that's the denominator g of x squared.
Okay.
Any other questions from today? Sounds like that's it.